All right. Well, good afternoon. Good morning to some of you guys, and welcome to Bruker Daltonics Demo Lab in Billerica, Massachusetts. My name is Pierre Mbarushimana, so I'm going to be walking you guys through our polymer analysis workflow with MALDI TOF. So we'll have a few things to talk about in the next 45 minutes. Just a few things to note is make sure that you adjust the different screens, the different windows that you have from webinars, just to make sure that you have a better view of the analysis that we'll be doing today. And also, lastly, do not wait up until the end of the demo to ask questions. So you should have a box somewhere down there where you can submit your questions as the demo is going, as it comes to it. So let's get started. Just a quick outline of what we're going to be looking at today. We'll start with an introduction to Bruker MALDI workflows. I'll give you a short tour of some of the instruments here in the demo lab. And then after that, we will go through the workflow where I have prepared a sample for us to use as today for the demo. So we'll go ahead and acquire some data, use the acquired data and process it through every software that we go through and use, and just show you all around and everything that we do for polymer analysis. So just a quick demo around what we have. So I'm sitting right next to the Autoflex Max, which is what we're going to be using today for the analysis and for the demo. But right behind me, if the camera will cooperate today, you guys can see that we have that horizontal diagram, which is our Ultraflex stream. So, and it's the third one on the slide that you guys can see. And then in front of me, the camera is a bit slow, but we'll get there. We have that tall standing Rapiflex, which is lurking, which is just coming into view. And then next to it, there's a few other instruments, so the TeamStop Flex and the TeamStop Pro and a few other LC ESI TOF instruments. Let's come back to the presentation. So we have 3 levels of instrumentations basically when it comes to MALDI TOF, and your instrument choice will depend on what kind of application you would need to be using it for. We have the Microflex, which is kind of which is our walk-up benchtop MALDI instrument, and it's a great option for simple polymer analysis experiments such as molecular weight determination, quality control experiments, or intact protein determination and things like that. It's very small, so it doesn't take too much of your space in a lab. Equipped with a 60 Hertz nitrogen laser, can be operated in positive and negative ion mode, and goes up to 300 kilodalton a mass. Next up in line, we have the Autoflex Max. So this is our all-around workhorse, basically equipped with and able to do any MALDI analysis that there is, including imaging, including MSMS experiments, which usually you need for structural elucidation or to be confident that the in groups that you've attached on certain series is what they are. And then next up to that, we have the Ultraflex stream and a Rapiflex. And these are higher specs, higher speed instruments. Um, Mainly the Ultraflex trim. This is our gold standard for polymer analysis. So for synthetic samples that are usually harder to ionize, are usually harder to see by MALDI, or that require very harsh conditions to be able to ionize, that's when you would need the Ultraflex trim. Of course, slightly higher resolution on Autoflex. And then top of the chain is the RapidFlex, which is more for if you're going for imaging experiments. This is equipped with the fastest laser in any MALDI instrument ever made, with a repetition rate of up to 10 kilohertz, and can see up to 1 million Dalton mass, M's of Z's. So just to get started, I wanted to go through some of the sample prep methods that you need before you get to the point of analysis for MALDI. Number one is the dry droplet method. This is the method that is more suitable for soluble samples. And basically what you do is you take your sample and you dissolve it along with the matrix, mix it pretty well, and then spot a droplet onto your target plate, like you can see in the image here on the top right side. So some of these samples have been spotted already and have dried, and these last two spots have just been spotted. So you only need a droplet or less of the mixture to be able to get usable data from it. And then similarly and commonly used, a commonly used method for MALDI sample prep methods is the double layer method. And this is slightly different from the dry droplet method in the fact that you have to deposit a thin layer of matrix on the target first, and then let it dry, and then mix your sample and your matrix together into one solution and deposit that on top of the thin layer of matrix that has dried already. And this is usually preferable for cases where you want to minimize the interaction of your sample and a target plate. And sometimes, depending on what sample you're dealing with, one of these will give you better results than the other. So if you're not getting pretty good results, you switch and try the other one and see what you get. The next one is a solvent-free method, and this is usually for insoluble analytes that are preferably in a powdery state, where you take the powdery sample, you mix it with the matrix dry, and then you vortex the mixture for about 5 minutes. You have to vortex it pretty well, make sure that you have a homogeneous mixture of both your sample and matrix, and then you smear a small amount onto the plate with a spatula just to make sure that it sticks and doesn't fall off when you introduce it into the instrument. And this is a nice image just to show how that's done. So you don't really need to have your sample soluble in anything as compared to most other techniques to be able to analyze it but MALDI. And then the last two sample prep methods, one uses a conductive tape to attach surfaces on a target plate or wires, such as you can see here in this picture on the bottom right, where we're looking at some of the coatings on these wires. So you attach your sample onto the target and then spray with the matrix, insert it into the instrument and start collecting ions from it. This is also another example. We had two pieces of clothing that we were looking at, one being a control and one being a finished product. And you could easily analyze it off of the surface with MALDI. We also have Tlc adapters and the glass slide adapters, which I'll show you in the next slide. And towards the end, if we have time, we'll look at our Tlc MALDI technology, which is proprietary to Bruker only, that helps you pair Tlc separation with MALDI for more detailed information on your mixture and your separated components basically from the TLC experiment. So these are the different sample targets, and I have them right in front of me. So we have the standard target here, which is what I've actually used for the samples that we're going to be looking at today, with up to 84 spots where you can actually drop your sample with the matrix on it. If you could see closely, hopefully the camera can zoom in and focus well. There's 3 spots here where we had used the solvent-free sample prep that I talked about in the previous slide, with just some powdery stuff on there. So I'm gonna go ahead and introduce this into the instrument while we look at the other targets. And basically, when you're done preparing your sample, you just put your target on there and then hit inject. Inject and eject in and out, just like you would a CD on a computer. Pretty simple. So that was our standard target plate. It comes in two sizes. So there's this standard one and a smaller size one that's used on a microflex. And then next up, we have the Inca chip target plate, which helps you concentrate your sample in a very small surface area. And what that helps you with is it increases the sensitivity by several orders of magnitude. In cases where you weren't able to see anything, you spot it onto the Inca chip target plate, and you get a much better signal from it. And then this is our TLC adapter, and as you can see, it fits in a TLC plate. So after you have separated your components on a TLC plate, you just put it into the TLC adapter, spray it with a matrix on top, insert it into the instrument, and image it pixel by pixel to see which components you have where on a TLC plate. And we'll have a chance to look at this in more detail towards the end. And then, so lastly, we have these 2 other targets that are usually for imaging. One that fits in 2 ITO glass slides for tissue imaging or biological sample imaging. And then also another direct surface analysis target that fits in larger surfaces, such as like this disc here, which was attached onto it using double-sided carbon tape and imaged as was after spraying with the matrix. So a little bit of an introduction of how MALDI works as a technique. MALDI TOF mass spec is a two-step process. And basically you have your MALDI process, which is the ionization step, matrix assisted laser desorption ionization. And then you have your TOF mass spectrometry phase, which is the second phase, where your ions that have been formed are separated into the TOF mass analyzer. So I have a quick video here just to show the inside of the instrument and how the ions are ionized, separated, and detected. So in the first step, once you have inserted the target into the instrument, you bombard your sample / matrix crystals onto the target with a laser. And then the sample molecules will vaporize into the vacuum, being ionized at the same time. And this step usually takes nanoseconds. It's a very fast step. And then after you've ionized your samples, you apply high voltage onto the target to accelerate your ions towards the detector. And that would be basically your first step, which is the ionization step. The second step is the separation step, or the where your ions are accelerated into the tube of flight. And basically, since you have the same voltage applied onto all the ions and you have the same flight distance, the ions get to travel at different speeds and separate into the tube of flight, reaching the detector at different times. So after separation by mass, in a linear mode, basically the ions will hit the detector within nanoseconds after the ionization, and lighter mass will arrive earlier than higher mass ions. And the flight time measurements per each ions are used to determine the molecular masses directly. So each peak that you end up with in a spectrum corresponds to a specific mass of a particle. And you can do this in two different modes. So you can do this in a linear mode and in a reflector mode. In a reflector mode, you have these reflector plates that basically will divert the ions so that they fly towards the secondary detector that you can see here. And this achieves two things. It extends the flight distance, giving the ions more time to separate, but also these reflector plates will help focus your ions onto the detector better than in a linear mode. And both of those two things make for higher resolution in a reflector mode than you would get in a linear mode. So that was a short introduction on how MALDI MS works. Next, we're going to go into data acquisition and analysis. Again, just a quick reminder, make sure you adjust the different windows that you have to make sure that you can see the softwares that I'll be sharing and also be able to follow along as I analyze some of these samples. So we have three softwares that work or that make up our polymer analysis workflows. And these softwares are integrated. They talk to each other from beginning to the end. So you don't have to acquire data, save it, and then have to go open up another software to process it. They all talk to each other. So as soon as you acquire data, it loads into the processing software and then into also our dedicated polymer analysis software. And these three softwares are namely called Flex Controlled, Flex Analysis, and then and then PolyTools in the end. So we're going to dive in and start with Flex Control. So this is Flex Control, which we use for data acquisition. So after you have inserted your target into the instrument, there's a camera inside of the instrument that shows you the spot where you have selected where your sample is supposed to be. You have also this illustration that shows you the different spots on the target that you've just inserted that helps you choose different spots, different samples. And since I know where my sample is spotted, I'm gonna go ahead and move it to our sample. And as you can see, you get an illustration of the target moving inside of the instrument as well. And then this big window here is where your spectrum will be loading as you analyze it. And then another window down here for the different settings of the instrument for different samples. So if you're analyzing a low molecular weight sample versus a high molecular weight sample, you'll need slightly different settings. But this is not something that you have to worry about because it all comes loaded into the different methods that carries all that information basically. So now that I have my sample in, I have three samples that we'll look at today. We'll look at PPG, which is around 1500 Dalton, another PPG sample that's around 2000 Dalton, and a polystyrene sample that's around 2500 Dalton. So that should be our PPG sample at 1500 Dalton. So, and to get started acquiring the data, all you have to do is click start. It's taking just a few minutes because the laser has to warm up a bit before it can start firing. And as you can see, right off the bat, I'm already getting really good results without having to adjust anything. So let's zoom in to see what we're getting. So it looks like I'm most likely using higher laser energy than I need, and you can adjust that here with this cursor. So we'll reduce the energy just a little bit in order to get better isotopic resolution. And as you can see, by adjusting the laser energy that I'm using, the resolution changes completely. And this is done by just moving the cursor up and down. And normally what I do is I will sum or collect multiple spectra from different locations, add them up together just to get a better signal and an average signal of the whole sample that I have spotted onto that plate. And when I'm done, we'll just save it into a pre-designated folder on a computer, PPG 1500, give it a name, save. And as you can see, as soon as I save it, it automatically opens up into Flex Analysis for processing. So I'm not ready to go there yet. Let me go ahead and look at our next sample, and this is PPG around 2000 Dalton. And this is also already giving me good results without having to adjust anything. As you can see here, we had a kind of a shift in molecular weight. So the first one was 1500 Dalton. Second one is 2000 Dalton. And I'll zoom in again just for better visualization to make sure that the method I'm using is optimized. And this is good resolution enough. I'm happy with this. So I'll go ahead and collect a few more spectra and average them. Add. As you can see, for each one of these spectra, it's only just taking less than a second to collect. So it's a very, very fast technique. And I'm happy with that. So I'll go ahead and save this one as well for us, our next step. And lastly, we're looking at polystyrene, which is slightly higher, higher in mass. And I have prepared a different method for that. So you usually have to change methods if you're looking at different molecular weights, but each one of this method come loaded with everything you need. So you don't have to look around for your sample. Start acquiring. And I'm already also getting a really good signal, pretty nice resolution as well, where I can see all of my isotopes. So we'll collect just a few more spectra and average it from different positions on a target for polystyrene as well. We'll save that. Polystyrene 2500. Oh, and just like that, I just analyzed 3 samples in less than 3 minutes. So once you are done, usually you'll have multiple sample preps, different variations, different concentrations, and you'll go through all of them and analyze them pretty quickly. And when you're done with the analysis, then we're ready to move on to our next step, which will be in flex analysis. So the data acquisition step is done, and we're going to look at some of the data that we have just collected. So flex analysis is Flex Analysis is our next software for in our workflow, which we use usually for common processing steps and tasks such as picking, such as baseline subtraction, such as smoothing, before we can import in the data into Polytools. So I'm gonna go ahead and do that. So we'll pick this sample a bit, and you still get another look just to make sure that you're happy with the resolution. And if not, you would go back to Flex Control one more time, and this looks nice. And I'll do that for all of our other samples. This looks good. Polystyrene as well. And once you're done pre-processing your data, so for this ones, since we're already getting really good data, we don't have to process it as much. But usually what I like to do is subtract the baseline from the sample, smoothen it just a little bit. Of course, we already picked it, so we have a mass list over here selected. And when you are done pre-processing your spectrum, you're happy with the way it looks, then you import the same spectrum into Polytool for further interpretation. And Polytool is our dedicated polymer analysis software, and this is where you basically get to calculate all of the interesting polymer characteristics that any polymer chemist is interested in. So things such as molecular weight, polydispersity index, the degree of polymerization of your sample. If you have different mixtures and different end groups, Polytool will give you basically a better understanding of what you have in your sample. And just a few windows here in Polytools, we have this big window that shows you your mass spectrum. The next window below that lets you input in some of the settings in regards to your sample that you may already know, such as what repeat unit mass are you looking for, what cations or counter ion did you attach on your sample, and things like that. But as you can already see, I didn't even have to put in anything. Polytool goes in and calculates and figures out the different series that I have present in the sample, and determines that we have a repeat unit mass of 104 for this particular sample, which would be correspondent to polystyrene. It calculates what the masses that correspond to the end groups would be. And then it also goes in and calculates the number average molecular weight, the weighted molecular weight, the polydispersity index, the degree of polymerization of each one of the series present in my sample before I actually do anything. It calculates all of that automatically. And then this last window here is our Kendrick mass defect plot, which I'll talk about in more detail in just a few minutes. But this basically helps you determine how many series you have in your sample. If it's the same series but different end groups, different polymers. So this is very useful for complex mixtures or polymer blends or different branching groups, different copolymer mixtures and things like that. So I'll go back to Flex Analysis and load a different sample, which is going to help us more with the understanding of how powerful Polytools is. So this is a different sample that I analyzed earlier, and is a mixture of both PEG and PPG around 2,000 Dalton. And as you can see in Flex Analysis from the instrument, it's quite a mess. You wouldn't be able to basically tell what kind of polymer you have just by looking at it. This will take days, probably with added to a headache after that, to be able to interpret and figure out what kind of polymer series you have in your sample. However, if we import this into Polytools, so I'm gonna go ahead and adjust the windows again one more time. As you can see, PolyTool automatically calculates and tells you what kind of polymers you have in your mixture. In this case, looking down here at the table, as you can see, we have two different types of repeat units, and one is PEG, which has a repeat unit mass of 44 Dalton, and then the other one is PPG with a repeat unit of 58 Dalton. So PolyTool goes in and deconvolutes the whole mixture automatically before you even look for anything that you may know to be in your sample. And if you wanted to have a little more control, better interpretation of the results, you can go back in here and remove the unassigned peaks or ions, and then also figure out whether we have PEG as a repeat unit, whether we have PPG, and various other repeat units that you would have: PET, nylon, PBT, PBMA, PVP. So all of these are things that you can analyze, PMMA, easily with MALDI and be able to determine them or figure if they correspond to what you're looking for in PolyTools. You could also go in and match it with different kind of ions, so sodium, potassium, different N groups, and calculate to figure out what's going on. So let's, for example, look at one of these series, which is a PEG series, and figure out what the N groups of this are. And I'm not quite sure if you, hopefully you have all your windows adjusted so you can see these small numbers, but if you click on either one of these series, PolyTool goes in and suggests what the different N groups for that series would be. In this case, it's suggesting a hydroxyl group with a proton terminating group, and then also a sodium counter ion, and calculates the residual mass to be 0. So I'm going to go ahead and apply this onto that series. And as you can see here, we go from a repeat unit mass of PEG, an original residual mass of 41, that gets reduced to a residual mass of 0 with the correct N groups. And if interested, you can go back in and look at each one of these series. So for example, for PPG, let's look at this one and see what PolyTool is suggesting. Also, a hydroxyl group and a proton N groups plus a sodium counter ion, and it calculates the residual mass down to 0, which tells me that those are the correct N groups for that series in the mixture. And we have quite a few other series present that MALDI can see. And this is one of the advantages of MALDI compared to other techniques such as NMR, for example, or GPC, which are bulk analytical techniques, which means basically they look at your sample as a bulk and tell you what they see. For MALDI, it's slightly different. MALDI basically gives you a molecular understanding of each ion that has been produced, and can separate different series, different N groups that attach to different polymer chains, for example, and things like that, and be able to separate them and tell you what they are on a molecular level. Now onto the Kendrick mass defect plot on the right side here. This is a feature that helps you better visualize the different components in your sample. I won't be going into detail how it calculates it, but basically you're able to choose a characteristic base unit for some of the series that you would be looking for. In cases of polymer, that would be your repeat unit mass. And if the characteristic base unit that you have selected fits, then any series with the same repeat unit will align the ions horizontally, whereas all the rest of the series that are not corresponding to the same repeat unit will have a different steepness or different slope to it into the KHMD plot that you produce. So in this example, I'm selecting PPG as my characteristic base unit. And as you can see, the bluish ions align horizontally, telling me that that corresponds to a PPG series. So anything that would be aligned horizontally would correspond to PPG series. And then anything else, such as PEG present in a sample that's not PPG, will have a different stiffness or slope, different from what PPG would have. And the nice thing here is you can actually export all of the data that you have fitted into the KHMD plot uh, for further interpretation or manipulation using other software such as Excel. And it gives you all the values, the intensity, as it corresponds to the M's of Z, the M's of Z fitted, and also your Kendrick mass defect numbers. So we'll look at this in a little more detail in the next few slides. But that's basically our workflow that's made up of the three softwares that I have just showed you. Flex Control for data acquisition, Flex Analysis for uh, processing of the acquired data spectrum, and then also PolyTools, which is our dedicated polymer analysis software. And as you guys saw, they all talk with each other. They're integrated together, so you don't have to load the data from um, your local folder and open up a different software to be able to look at it. It basically loads up into the different softwares as you're analyzing and as you go, and you can come back and change it if needed. So now moving back onto our PowerPoint presentation for a few more things that I would like to show you. This is a different sample that was analyzed using PolyTool, interpreted using PolyTool, and was a complex polymer mixture of PEG, PPG, and PMMA. And as you can see here, we get about 4 series present in the sample, 2 of them that align horizontally, meaning that they have the same repeat unit mass. And in this case, the repeat unit mass that was selected was PEG, so this would correspond to a PEG series. 2 separate PEG series with different N groups. And if you have a different polymer series with a different repeat unit, it'll have a different stiffness to it. In this case, PPG and PMMA, which would have different repeat unit masses. And this is very powerful because this can be done on thousands and thousands of on a polymer mixture that has thousands and thousands of different series. It's the same software, same feature that they use for the analysis of petroleum crude oil samples, for example, which could have millions, thousands and thousands of components into a very small mass range that are related and just have different small differences, such as different nitrogen content, different nitro content, different oxygen contents, different N groups, and things like that. This is another sample of a PET sample that I was able to use PolyTools on and figure out what the different N group masses are. And as you can see here in this sample, we have multiple series present, and I was able to easily identify up to 4 different N groups in here, which also give me a residual mass of 0 Dalton for each one of these series using PolyTools. Another really nice application for PolyTool is for QA/QC experiments. So this is when you were trying to basically compare 2 samples, for example, 2 samples from 2 different vendors, or the same sample but over a long period of time where you expect it to degrade, to experience some degradation over time, and you want to compare the before and after. This particular experiment was done on 2 PET samples from 2 water bottles. One was basically manufactured to hold cold drinks. The other one was manufactured to hold hot drinks, cold and hot drinks. But both of them are PET samples, basically. And by just looking at the mass spectra, they have the same series, they have the same N groups. So there's really nothing to tell that would be different, the same average mass as well. However, if you plug them into PolyTools and generate a KHMD plot from both of them, you start seeing the minor differences that you wouldn't be able to see otherwise. for these two samples. So as you guys can see already, we have the same number of series, up to 8 series. And if you look deeply on each one of these series, let's take series number 8, for example. In sample A, as you can see, this extends from 500 Dalton to about 4,000 Dalton. But in sample B, it's extending from around 800 Dalton all the way up to close to 5,000 Dalton. Same series, same N groups, same polymer, same repeat unit, just different mass range. And then also, let's maybe pick another one, series number 1. In both samples, present exactly the same repeat unit mass as well. But if you look closely, as you can see, the dots are a lot less intense in sample B than they are in sample A, telling us that this particular series is more present or more dominant in sample A than it is in sample B. So lastly, since we have a few minutes, I wanted to introduce you guys to our TLC MALDI technology that we have developed here at Bruker. And most of you are likely familiar with TLC, thin layer chromatography. This is an indispensable separation technique in most labs with a number of applications in forensics, in food analysis, in clinical and industrial applications. Just because it's a quick and simple way of determining what kind of components you have in your mixture. However, this has a lot of drawbacks. One being that it's time consuming, for example. So you have to, after you separate all your components, you have to separate them using chromatography to be able to analyze it with a different technique, such as NMR or another technique to be able to figure out what those components are. And another thing is that they basically use a lot of resources, such as your columns, solvents. Over time, this all adds up to a bigger cost. And what we've been able to do is basically couple TLC as a technique to MALDI, where what happens is, as you saw on a previous slide, you can run your TLC separation on a TLC plate, plug it into the Tlc adapter target for MALDI, insert it into the instrument, and then image the whole TLC plate pixel by pixel to figure out which components are located where on your TLC plate. And what you generate is this heat map that you can see here. So on the left side, we have, this was done on a standard lipid mixture. And on the left side, we have a UV detection of our TLC plate, where you can see the different bands present in your mixture. But although you can see the different bands, that you have also separate them nicely, you're not able to identify the different compounds under these components that you see on the UV. And another thing is that most samples will be similar in structure and have the same polarities, interact with the TLC plate exactly the same way, have exactly the same retention RF values, and be embedded under the same component or the same dot, the same spot, making it hard to determine how many compounds you have in your mixture. With TLC MALDI, you generate this heat map that has your M's of Z's as your x-axis, your RF values as on a y-axis. And if you look deeply, you can see that, for example, in one of these red spots, that we were able to see up to 4 compounds that are co-eluting on a TLC plate, which is something that you wouldn't have been able to separate basically by chromatography. Same goes with the other dots, where we have 2 components in his purple component, for example, 2 other ones on PG. And this is basically done in a matter of a few minutes, very simple, and you can determine all the components with more confidence to know how many you have that are co-eluting or not co-eluting. even further, you'll have the ability to select a precursor ion on each one of these components, and then perform an MS-MS experiment on it for structural elucidation, so you are more specifically confident that that's the compound that you are seeing on a TLC plate. And lastly, this is not something that's only for small molecules or lipid mixtures. This is something you can also do on polymer mixtures as well. For example, in this case where we have two pegs, one is branched peg sample, glycerol-ethoxylate peg sample, and the other one is a linear methylated peg sample that were nicely separated on a TLC plate. And with TLC MALDI, you're able to see them as well, highly resolute at different masses. And with the MS-MS capabilities, be able to determine whether you have a linear peg or branched peg off of a TLC plate MALDI as well. So generally for branched peg, due to the fact that you have different arms that will break off and produce different fragments, you end up with a fragment mass spectrum with multiple distributions. Whereas for linear polymers or linear peg, you only have a single distribution in your fragment spectrum. And this is something that you are not able to differentiate just by regular MS MALDI analysis. So in conclusion, some of the advantages of MALDI TOF MS for polymer analysis. Hopefully I've been able to convince you that MALDI is a very simple and de-skilled technique with fast adaptation, that it's a very fast analytical technique for polymers. In just about 5 minutes, you're able to basically know what you have in your sample, and those 5 minutes comprise about 4 minutes for sample prep. The data acquisition step itself is only just a few seconds. It gives you direct access to molecular weight, as well as N groups as well. Very flexible technique for difficult and insoluble analytes. You don't need to have your sample dissolved in any types of solvent to be able to analyze it using MALDI, as opposed to other techniques used for polymer analysis. And it also comes with a complete package of industry standard softwares such as PolyTools, like we saw, Flex Control and Flex Analysis for data acquisition and data processing as well. Some of the other applications, aside for polymer analysis, in TLC MALDI, you can also use MALDI for top-down sequencing of proteins and peptides, for imaging experiments, as well as proteomics LC-based experiments, and MALDI Biotyper, which is also another line of instrument that we use for QA and QC applications. Also, not to forget that although we looked at MALDI today, we have a large portfolio of other instruments as well, from high resolution LC QTOFs to ion mobility instruments, and also routine LCMS and GCMS instrument that you have available from Bruker, all supported with industry standard softwares and other add-ons as well that you can be able to get from Bruker. And with that, I'd like to thank you for your attention, and I'll take any questions if there are any for the time remaining that we have.
Thank you, Pierre, for this very informative demonstration. Very nicely done. Indeed, we have some time for questions, and we have received quite a few. We'll answer as many as we can in the remaining time, and the rest of them we'll make sure to answer in separate emails. So let's start with what we've got so far. Would PolyTool be able to identify for mixture of polymer if is only different in the N group?
could you say that one more time? 4 different
Yeah,
mixtures?
I'm trying to read it here.
Right,
Would
right, right.
Polytool be able to identify for mixture of polymers if is only different in end groups?
Right, yes. Yeah, Polytool, even if you have the same sample, for example, the homopolymers, um, I can pull up Polytool maybe just one more time for here. So if you have a homopolymer with different end groups, you should be able to see the different series with the different types of end groups that are attached to it as well. So for example, here, as I show here, we have only 2 polymers in this mixture, so PPG and PEG. And for each polymer, there's different end groups. It's rare that you have a synthetic polymer that only has one type of end groups with no side reactions, with no other end groups in the mixture. Um, so you would always be able to tell the different series apart if they have different end groups. Yes.
Thank you, Pierre.
Yep.
So next question. Can the software handle protein analysis, such as peptide sequencing?
Polytools.
I suppose any software in general that we have in our portfolio.
Right. Not Polytools or Flex Analysis, but we do have another software called BioTools, which we use for sequencing of proteins and peptides, identification of intact molecules, and everything that has to do with proteins. Yes.
So I think I will add that this is slightly out of scope for this particular demonstration, but yes, MALDI is routinely used for protein analysis, and there is a dedicated software package for those applications.
Right. Yeah.
So next question. Can powder sample harm the ionization chamber after laser shot?
That it depends. Normally, using the sample prep methods that I've shown, that there shouldn't be any issue in the ion source. But there's some requirements that we have to abide by, especially for insoluble samples or polymer surfaces. So it can't be something too thick. For example, you need a sample that's at least 5.5 millimeter or less in thickness. Anything bigger than that will definitely defocus the laser and damage the instrument. But other than that, as long as you can attach it onto a target and it doesn't exceed that thickness, you should be able to ionize it and analyze it without any issues with the instrument.
Thank you.
Yep.
Next question. For insoluble samples, how do you apply the sample to the plate without scratching up the MALDI? Without scratching up the MALDI plate? The scratching will affect the performance of the plate since it will no longer be a smooth flat surface. Can you comment on this?
Right. So our target is ground steel targets. So they're pretty robust, pretty hard and durable. So unless you're scratching it with a metal really, really hard, there shouldn't be any issues with the target. And usually to apply so there's 2 types of insoluble samples you can apply on a ground steel target. Something that's powdery mixed with the matrix, and all you need for that is just a little bit of that mixture, and you smear it onto the target pretty lightly. So that definitely won't cause any harm on the target. And also, if you have a surface and it's taped on there, you can easily remove it. Um, and I've used the same target for very long periods of time. Barely had any chipping or any changes onto how the surface of the target looks. So it's pretty. You would have to put some effort and energy into it to be able um, to chip the target.
Thank
Hopefully
you.
that answers the question.
Thank you. Next question. How to make a matrix choice for polymer sample, and at what ratio we should add it with the sample?
Good question. Good question. So especially for polymers, there's no proven one matrix for one type of polymer that available. Usually, you have to do a little bit of research and see if anyone has analyzed the same polymer, especially if it's a synthetic polymer that has never been analyzed before. But there is an NIST library or link that I can share with the interested person. It's usually MALDI.NIST.gov that has quite a plethora of different types of sample preps and conditions for most of the polymers that have been analyzed up to this point. For something as PEG or polystyrene, that should be pretty easy. There's quite a lot of choices, such as you can use DCTB or Dithronol for polystyrene and things like that. But you should be able to find some starting conditions to use that also includes the sample to matrix ratios that you would be using. And usually for as a starting point, you want to have more matrix than the sample, because the matrix is what's going to absorb the laser energy and then in turn transfer a proton onto your sample. So usually we have starting point up to like 20 to 1 stoichiometric amounts of matrix to sample, but it varies again per sample, per molecular weight of the polymer, and things like that.
Thank you, Pierre. Another question about TLC techniques. Are these normal silica gel TLC plates?
These are aluminum backed, yes, silica gel TLC plates.
Thank you. Next question. Were MS images automatically generated? So I guess they came directly from the instrument in that sense.
Yeah, that's quite broad. That's quite broad, but we use for the TLC MALDI imaging, we have a dedicated software for that. Comes with the instrument, it's free, and it's very easy to use. And it actually does. All you have to do is just set the different points where you want to image from what point to what point on a region on a TLC plate, and it will image it automatically and generate an image for you without having to do anything. I'm assuming that was for TLC imaging. The question.
That's what it sounds like.
Yeah.
Next question. When do we add matrix for TLC MALDI? Do we add the MALDI solution on TLC after the separation?
Yes. So you add the matrix after the separation, and there's different ways of applying the matrix. You can spray the matrix on top of it, or you can dip it into a MALDI matrix solution as well. So there's different matrix application techniques that we can look at in more details. But yes, that's done after the TLC separation step is done.
Thank you. I think I will take the next question. Can you make demos showing how the various sample preparations are performed? For example, dry deposit, sandwich method, etc. Yes, I think that very well could be our next demo.
Yes. Yeah.
So I think we're right around the time allocated for this demonstration. Once again, thank you very much, Pierre, for this excellent demo and very informative presentation, as well as answering any questions. Those questions that we didn't have time for in this live presentation, we will make sure to answer in separate emails. Thank you for your attention.
Thank you. Have a good one.